Hello, and now we are talking with Dr. Josef Uyeda, who is a professor in Virginia Tech's Department of Biological Sciences, who studies trait evolution amongst a wide variety of organisms. Josef, if you'd like to introduce yourself briefly and kind of what all you work on.
Yeah, so I'm an assistant professor in biological sciences. I'm an evolutionary biologist, and I kind of started working on microevolution and became interested in how that scales up to longer time scales, million year time scales, and looking at patterns we see across the tree of life. People in my lab work on all sorts of different organisms, ranging from birds, bees, plants, all over the place. Basically, we're just interested in reconstructing how traits evolve, what they respond to, be that climate or coevolution or whatever the process is. And our goal is to just kind of make sense of these patterns that we see across biodiversity in terms of the processes that generate them.
And so, from what I understand, you and your research group do a lot of this research through statistical methods related to phylogeny. In your work, do you tend to use more genetic phylogeny or phenotypic character state phylogeny?
Mostly genetic phylogeny, although there's absolutely a role for the morphological data in reconstructing the phylogeny, especially, obviously, as you know, for fossil taxa. And those fossil taxa can be often the key piece of information that can distinguish between different possibilities, different models of evolution. There's a limit to what we can say only having extant living taxa. And so having the fossils can really be helpful.
Can fill in some gaps in the evolutionary history.
Yeah, absolutely.
Cool, cool. Would you like to tell a little bit about kind of your academic background and how you came to be working here at Virginia Tech?
Yeah, so how far do you want me to go back?
As far as you'd care to.
All right. I mean, I was always interested in biology or living things and kind of was an obsessive kid about some topics. But I was also not, I think, on the track to be an evolutionary biologist. I didn't know exactly what I wanted to be. I actually was a creationist in high school and entering college, actually. But biology classes quickly changed my view. And I think I was drawn to kind of systematics research because, figuring out like all the different organisms that are out there. I was really into herps, so frogs and salamanders. And I did some internships. So I did internship at the Summer Systematics Institute at Cal Academy of Sciences. I worked with Bob Drews, had a great time there. We did some molecular sequencing of some frog species from some little African islands, Sao Tome and Principe. Ended up describing a new species of frog from that, which is, one of the most fun scientific accomplishments to this day that I've had.
What is the species called?
So it's called Phrynobatrachus leve. So it's a tiny group of these frogs are tiny. They're like the males are like 10 millimeters long, and the phrase leve is a phrase that's used by the Portuguese speakers on the islands, and it means kind of the equivalent of easy, or lightly. It's like go easy, kind of, and it's kind of a bit of a motto of the islands, I guess. And so we wanted to give the frog that name to kind of characterize the unique and culture that's on the islands. Yeah. So, and then from there, I knew I was interested in grad school after that, getting into research. And I joined the lab of Steve Arnold at Oregon State University. And going into that, what I was blown away with right away was kind of all the theory of evolution that I had not, I guess I hadn't realized how quantitative, and once you knew the math, it was just like, wow, this just falls out, right? And this explains so much, and how could you, this seems like such a powerful framework for understanding how change occurs. That lab focused a lot on kind of quantitative genetics theory, which is a microevolutionary theory for understanding trait evolution in response to natural selection, genetic drift, all these microevolutionary processes. And we were interested in just taking it to, okay, what happens if you just take these microevolutionary equations that work incredibly well, like you can experimentally validate them, they predict evolutionary change over short time scales quite effectively. What if you just scale those to a million years, or you just run this forward and let it go. And so there's some paradoxes that kind of emerge from that, or some things we need to understand how that scales. And so for my postdoc, I wanted to work from the other side.
Where did you do your post?
Oh, I did my postdoc at the University of Idaho with Luke Harmon. And so that's where I got into the kind of macroevolution phylogenetic comparative scales. I wanted to learn these methods that were top down rather than bottom up that I had been exposed to previously. And so I wanted to kind of learn these methods and work them kind of back down to the microevolutionary scale so that we could maybe connect the two. And so that's kind of been a lot of the motivation that inspires my work, is to try to work at these two different ends and try to bring them together. And the issue is a lot of times just connecting the dots, right? We see these patterns at million-year timescales, but we can't rerun them experimentally. There's some limitations to what we can do. The microevolutionary studies are really effective, but we can't play them forward for a million years. So you kind of have to reach from both ends to try to fill in this missing piece for which we have data, but it's maybe not the best data just given our limitations with time.
Our experimental studies are great, but they're a little bit harder to apply to organisms whose generation time is longer than like a month.
Right. Absolutely.
Well, one thing that I think is very valuable about your research and how it applies to teaching people about biology is it really kind of bridges the qualitative and quantitative aspects of biology as a science. Those often feel a little bit binned from each other in terms of how they're taught. And so do you think that phylogeny and other methods that you use are very useful for integrating quantitative and qualitative aspects in undergraduate education of biological sciences?
Specifically for undergrad, what do you mean for undergraduate education, I guess?
In the sense that, do you feel that introducing these sort of phylogenetic concepts helps students combine thinking about quantitative aspects of biology with qualitative aspects of biology?
Yeah. So I think, that the phylogeny really gives you a framework for understanding the patterns in biodiversity that we see. And so, it's definitely something that we teach and I teach in my intro courses, and it's useful. But at the same time, I think that, it doesn't need, yeah, exactly like you're saying. I don't necessarily think you need a quantitative grounding or to be good at math to understand the phylogeny, right? It's just being able to kind of make sense of how evolution has occurred through the past and like what it actually means, right? And I think that takes quite a bit of work. There's a lot. It's easy to misunderstand what a phylogeny means. It really takes kind of playing around with it and to make sense of it. This tree thinking, as folks talk about, is something that is not always intuitive immediately, how you are representing, and it's not surprising. It's how you represent millions of years of evolutionary change. All of biology basically is crammed into this little connect the dots line drawing on a page, right? And it's like, how do you capture all of that biology with this little diagram? Well, you're not going to, but you hope that you capture something that's really important, which is common ancestry and descent over time.
So over the course of your academic career, how have you seen your responsibilities change and progress? And how do you expect those responsibilities will change as you get deeper in your career?
Yeah, I mean, like everybody, I guess, you go from being a student, learning. Your job is to learn. Your job is to follow, directions. To doing the science yourself, starting to formulate your own questions, carrying out the research yourself. As a postdoc, your full-time job is to just do research. And then as you become faculty, it becomes much more of your time mentoring and organizing and writing grants, and not necessarily always doing all of the research, but helping people in your lab, helping your collaborators, working as part of a much bigger group, a much bigger team to kind of get science done. And then also, things like I just became an editor this year, service. I serve on the Biological Sciences Diversity Committee. So
Which journal do you edit for?
Systematic Biology, associate editor.
Nice.
So yeah, each of these things, you kind of move to being more the role of organizing and supporting people so that they could do science and mentoring them and teaching, and less directly doing and having enough time to do all of the science that you want to do.
So I guess to kind of drill into editorship a little bit more, since I will admit I have a broad idea of what all editorship entails, and that you help organize peer review and that important review process of determining ultimately what gets published and how to ensure that only the highest quality material gets published. But what other roles does an editor play? Like, do you have input on kind of the direction and overall vision per se of the journal that you edit for?
I mean, I guess to the extent that you make recommendations on whether a paper is accepted or not, that you have to have some idea of what's appropriate for the journal or what the goals are for the journal. This is not something I've been doing for a particularly long time, so I'm by no means an expert on this. I'm quite new to it, really. But I think the most fun for me so far has been kind of like finding reviewers, and that's challenging because everybody's so busy right now. But one of the most satisfying things is kind of like finding early career researchers who maybe aren't in the system yet, maybe haven't reviewed for the journal yet, but whose research is relevant to whatever, paper is being submitted, and bringing them into the process, and finding who those people are and kind of learning about everybody's research, going through people's web pages and learning about like all the great work that people are doing. That's been the most fun so far. And in that sense, I think it's kind of, you do have some power as an editor to bring some people into the process, right? So
in my earlier talk with my advisor, Shuhai Zhao, we were talking a little bit about editorship, and I made the comment that in some ways, editorship is very useful for early to mid-career faculty, in the sense that it's a very good external way of keeping you abreast of what all's going on in your selected field.
Right.
Kind of forcing you to, lick your finger and stick it in the wind and see which way the wind's blowing.
Yeah, I mean, it definitely is kind of the next step up from, just reviewing papers, right? Because you get to not just give your feedback on the paper that comes in, but you get to solicit feedback from reviewers and identify reviewers, do all this research on the people, right? Whereas when you're reviewing a paper, you're usually just focused on the content of it. So yeah, it definitely helps you branch out more.
So one thing I want to get into a little bit in this interview is kind of how you anticipate or what you would like to see in terms of changes in academia. And since we're talking about editorship, I think that this would be a good chance to talk about the open access movement in scientific publishing. And what kind of changes to open access would you like to see from journals in general?
I'm a big advocate of society journals like Systematic Biology that have control in, so I guess, I definitely am a supporter of the open access movement. I think that I would like to see a move towards, I just think that that access is really poor right now, and that we have such a premium on having a few journals that we view as high impact and being important for people's careers. And I don't always think that the quality added from having our libraries spend so much, and having people who are just want access to a single article having to spend so much is really adding a whole lot. And I think that when societies run the journals, they're more focused on the scientific mission, and the whatever costs are involved are going to support a society, which then goes on to support its members, right? So yeah, I guess for me, I feel like too much emphasis is placed on clearing a bar to get it into a high impact journal, rather than just focusing on the quality of the science and contributing to the progress of science, which I think the society journals do a really good job of doing.
And I think kind of one of the other benefits of society journals is that in some way they kind of help combat the increasing consolidation of journal publishing, and that now it's 3 or 4 publishers like Elsevier, for instance, control upwards of 80% of all scientific articles that are published in all fields. And that's really kind of troubling in a way. People make the classic argument for open access and that so much research is publicly funded and publicly supported, but so little product of that research is publicly available.
Right. Yeah, absolutely.
Kind of stepping back from that a little bit and getting a little bit more broadly, within the university, how do you expect the future to change universities and students' expectations of professors and of research?
Kind
of a broad question. I can give you a moment to think about it.
And nothing. Yeah, I guess I don't have any grand insights to that, other than that, the expectations I think are that we're training people for the jobs that will exist, or we're giving them training to be successful in whatever careers they choose, and so I think that one thing that we probably need to do a better job of is that so many of us know the academic path because that's what we took, and kind of train people for that path because that's what we're familiar with, and we really need to diversify our conception of what possible paths there are, and also need to know what all those paths may be, which requires a little bit of foresight and prediction, right? So it's not an easy thing, certainly, but I think we need to do a better job of kind of training for what the careers are that are out there in science and STEM, at least for, speaking from my field. So, in my work, that kind of takes the form of trying to give people, they may be working on a very specific evolutionary question, and they may not be thinking about going into evolutionary research, right? But trying to give them a training in, data science and statistics, and just giving them some useful abilities to use quantitative reasoning and some skills that'll be potentially useful in a lot of different jobs. You never know which classes and which experiences are going to lead to something that becomes your career. And so just being open to that, I think, is really important. So that's something I think we can continuously improve on. Is that kind of what you were getting at with that question?
You talked a little bit about teaching introductory classes to undergrads, and I thought I might ask you a couple of questions about that. There are difficulties in every class, and one of those things is sometimes communicating and getting students to understand certain technical ideas in a way that is correct, but also gives them building blocks to build on future ideas and future classes that they'll take. What are some of the concepts that you've generally found more difficult to introduce and explain thoroughly to students?
Yeah, so one of the hardest things is exactly the quantitative reasoning, right? And I think there's a lot of anxiety and built-in discomfort with math, right? So I know that that's one of the hardest things when I introduce that into my evolution course, right? Just teaching about very simple, but can be quite, the hard part of the math is not usually the math, right? The equations that I use and I teach are very simple, and almost everybody has had the math training that in their life to understand them, right? It's really not challenging. What is challenging is taking the math and understanding what that represents in the real world, right? Drawing that line between the biology and this quantitative thing and understanding why this is useful. And so that's what I try to emphasize is less. I don't really care if you can solve integrals or whatever. I want you to be able to, describe in words, what does this mean? What is, be able to understand the meaning of this. And I think that is a challenge, and not really how we teach math, right? It's hard to learn quantitative theory and math and all these things when you don't have a motivating application, that you don't have something that you're trying to figure out, right? As soon as you go, I see this over and over again, that people, when they go to grad school, then they are faced with a problem that they're faced with solving, and they're like, oh, now I get it. Now I need to learn this statistics, right? I need to learn this math so that I can solve my problem, right?
I'll certainly admit I regret not taking more statistics courses as an undergrad.
Right. So, but that's how it should be taught, right? You should be faced with a problem that you want to solve. And then you're like, oh, well, now I need to this is why I have to learn how to do algebra and calculus and whatever it may be. And so that's I think the biggest challenge is also just because there's so much anxiety and also, our culture has communicated so much inequality about who is good enough and who is capable of doing math and who's not, that it's a challenge for that reason. But I think it's important for people to see it work and get some confidence that it doesn't require you to be a brilliant, like it just requires you to have the patience and to make the effort, have someone teaching you that kind of makes those connections to the real world for you, right? So
On kind of a similar note, one thing that I wish I had gotten a little bit more practice with in my undergraduate classes was the use of programming and calculating tools like R. I used it maybe once or twice in a couple of classes, and I set aside some time as an undergrad to use it for different things. But I often find now in grad school that like I have a problem or a graph that I need to make in R, and I'll read up on how to do it. And for like a period of a couple of weeks, I build up a competence of R, and then I set it aside for like a month or two when I'm working on other things. And then when I come back, I remember very little. I remember a little bit more each time, but
Mhm.
I often wish that I had kind of built up that backstop of R competence a little bit higher than undergrad.
Yeah,
So I'd like to see R integration and Python and other
right.
tools that we as research scientists use integrated a little bit more into different classes.
Yeah, I mean, I didn't know programming before going into grad school, and I was lucky enough to have a stats professor who, at the time, all the stats courses were taught in S plus with mostly like a graphical user interface. But he also gave the option. S is the same, the source of R, which is free, and I didn't want to pay for a stats program. So he gave all of the lessons in R as well. So I learned through the course of that stats course, and then just started doing it in my research and thought it was quite a bit of fun. And thinking about like what kind of made me like not kind of dive in, I guess I was used to a command line, even though I wasn't used to programming. I had, my dad didn't buy us, Nintendo or console games. He bought us like a DOS machine where if I wanted to play the game, I had to like search among these directories and figure out where he hid it, and like do all this stuff by command line. And that's all. So I was like, oh yeah, I know how to do this. Like, but I didn't. But you learn by trying. You learn, and at a certain, once you've got that kind of base level of the language, then you can really start taking off and building on it, right? So it's like any language, you feel completely kind of helpless until you get that base level of understanding, and then you can kind of take off. So
As a person who oft feels very helpless in R, who spent a lot of time searching on the internet, how do you do X in R? I've found certainly enough forum posts to understand that no one really has a complete grasp of the entire grammar of that particular language.
you
And
never stop searching for on
yeah,
Stack Overflow.
yeah.
So,
And in some ways that is kind of relieving in that you see that basically everyone else finds it as frustrating and as difficult as you do. Like I
right.
remember one of the things that befuddles me and that I still could not do entirely properly right now is so as part of my work I do a lot of chemostratigraphy and stable isotope chemostratigraphy, and so I need to be able to put the delta symbol into a lot of different places on a graph, and
Right.
in R, depending upon what you're using, the way that you put the delta symbol in a title versus a legend versus an axis title are very, very different. You can't use the same way each time.
Yeah. And I remember none of them. So
Yeah, yeah.
I have to look it up every time.
And the places that I find out how to do that, it's not the same place. And none of those individual places tell you that this won't
Yeah.
work in the other things. That's just something that you put together painfully.
Right. Well, I mean, as somebody who like is making R packages for other people to use, like there's nothing more humbling and that makes you more sympathetic than making something for other people to use.
Yeah, the
And
people who make our packages like that, those are the real MVPs.
yeah, right. I mean, we're not. There's a big community of people that are like me, which are not computer scientists, not programmers, who are biologists who try to make these R packages, and we're not, necessarily good at making beautiful streamlined code that everybody could understand, read, modify, and use without error, so we make mistakes, we do some things that don't make sense in retrospect, but it's not out of malice, it's out of we're
R is
just
a
trying to
lot like,
figure it out.
and programming in general is a lot like evolution. While there are, parsing functions, so to speak, that pare things down to their most efficient things, it's very much an good enough type process in
Yeah,
most cases. If you
right,
get something that works, you don't have to poke around too much inside.
right. I mean, that's the value of it, right? Is that so often, the kind of the philosophy of my lab is that, probably the out of the box comparative methods or whatever statistical tool is available may not be exactly what you need as a scientist. Like, you have this extra bit of data, or different source of data, or you have this idea of how this process works that doesn't fit into the, it's a square peg in a round hole sort of thing. And so having the ability to tinker with the machine, right, get under the hood and, like, oh, just if I just cross these wires here, now I can have this tool that actually works for what I want to do, right? That's kind of the goal, so that people can be independent and free of the constraints of the tools, so that they can actually answer the scientific questions they want. And I think that's a really important avenue for progress in training scientists and training, people to do any kind of job, is that oftentimes the tool that's available is maybe close, but it's not quite perfect for the job, right? And so that's going to be a lot more common, I think, in the future, is that people will kind of have customized analyses for their question, rather than having, just relying on out of the box tools and making sure you satisfy the checklist of assumptions, which you probably won't, but hope that's not too bad and try to use it anyway, that sort of thing. So that's what we try to do in our lab, is to train people to be able to get under the hood and tinker with the machinery enough to get what they want out of it.
Nice, nice. Well, thank you for your time and your perspectives today, Dr. Uyeda.
Yeah, no problem. Thank you for having me.